According to the principle of source transformation, any branch that includes a voltage source and a resistor in series can be converted into two branches in parallel composed of a current source and a resistor by retaining the value of the resistor and converting the voltage to the current using the equation V equals IR or some other rendition of this equation. For example, suppose we wanted to analyze the following circuit, which has a current source and a voltage source. We could probably use some kind of combination of KCL at this node and KVL in this loop, but instead, let's use source transformation to get rid of this current source and turn it into a voltage source. Observe from the diagram that we can perform the conversion if this current and resistor in parallel X are the only things exiting point A and the only things entering point B. If we select a point A and point B here that look like this, you can see that we have a current source and resistor in parallel that can be converted into a voltage source and resistor. According to the equation, the voltage of the new source has to be equal to the current of the old source times the resistor in parallel. So the voltage source equals 3 times 3 equals 9 volts. Thus, according to the diagram, we can convert the current source and resistor into a 9 volt and 3 ohm resistor in series, and thus we get the following circuit, which actually becomes wonderfully easy to analyze. If two voltage sources are in series, even if there's a resistor in the way, you can combine them. If two resistors are in series, even if there's a voltage source in the way, you can combine them. So we can make this circuit into a 15-volt battery and a 15 ohm resistor in series, which means that the current through this circuit is 1 amp. The last step is to decompose this circuit back into its original form so that we can find out what the values of the resistors and voltage and current sources and such were. Note that because these two circuits are the same, this circuit also has a 1 amp current. If we call these 2 points A and B, we can locate them on this changed circuit as A and B. In the two circuits, everything on the right of A and B is the same, so in this circuit there must be a 1 amp current on the right of the points B and A. If we do KCL at this node, we observe that 1 amp enters it from the right and 3 amps exit it from the left, so there must be 2 amps entering it from this middle branch, which is interesting. But this should make sense. If we look at KCL up here, we see that 3 amps enter the node, 2 amps exit the node in the middle, and 1 amp exits the node on the right. Knowing these currents, we can now assign voltage drops. We see that there's a 12-volt drop across this 12-ohm resistor, and the voltage drop across this 3-ohm resistor is 6 volts in this direction, downward. If we do a quick check with KVL with our loop direction this way, we see that we have a rise of 6 volts, a drop of 12 volts, and then as we walk up this direction, we go from a negative to a positive and rise by 6 volts. This equals 0, so it looks like what we've done is correct. Our analysis of the circuit worked. In order to use source transformation effectively for the analysis of a large circuit, you need to be able to decombine your circuit. So if you've combined and transformed, you need to be able to untransform and transfer your data from the simpler circuit to the more complex circuit. Or you can perform your source transformations to isolate the specific resistor or voltage source or whatever that you want to get data about. If we wanted to get data about this 12 ohm resistor, we don't need to combine everything. We can just combine only up to the point that we retain the 12 ohm resistor in the circuit, and then find out what the information is about that 12 ohm resistor. As long as the resistor is intact, we will make correct observations about it, and we don't need to decompose the circuit to still make those correct observations. Now, to explain why source transformation works, we're going to use the theorem of superposition that we learned in a previous video. Why on earth should this be exactly equal to this? It doesn't seem to make a ton of sense when you first look at it. Let's imagine there was a whole bunch of stuff on the right of B and A. And let's imagine that in the principle of superposition we ignored this voltage drop. That means there's just this one resistor, and all the stuff on the right applies to the stuff on the left and shoves some kind of current through this resistor. That current probably produces some kind of voltage drop across this resistor. We'll call that voltage drop the voltage drop due to the outer part of the circuit. Now suppose all the stuff happening on the right of B and A here is also happening on the right of B and A here, and let's perform superposition again. In superposition, we treat this current source as if it was a broken wire, so the only thing that any of the stuff on the right can go through is this resistor. That means, just like on the left, everything on the right side of the circuit will only go through this resistor when we perform superposition. Everything on the right side of this circuit will go only through this resistor when we perform superposition. Thus, we can again say that across this resistor there is a V outer, an outer voltage corresponding to everything happening on the right side of the circuit. So the first thing we discovered using superposition is that these two resistors behave identically no matter what's on the other side of the circuit. So we can convert this and make it look like, we can convert the left side to look like the right side, and the resistor will still have the same effect from the outside of the circuit. But what about the voltage source? Why can this voltage source be equated to a current source and a resistor? To understand this, we must first understand that any current which enters A must also exit B. This is true no matter if there's a voltage and resistor or a current and resistor in parallel. The reason for this is, let's put A and B in an actual circuit. According to KCL, let's say some current enters A, and then it can exit off in either of these directions. All the current that goes through R2 will re-enter the circuit at B. So, all the current that exits from point A must also re-enter the circuit at point B, the same amount. This is true even if we converted the voltage and resistor into a current and resistor. If A and B are put in the same place, we see that if current enters here, any current that exits upward must enter the same amount into B. So any current which enters A in this section must exit into B up here. What this means is that in this version of the circuit, if any current enters A, that exact same amount of current must enter B, so all of the current from this current source must actually flow back down through the resistor in a perfect loop so as not to accidentally create any new current. All the current coming into the circuit from A must exit the circuit in B. If all the current that comes from I goes through R, that means that there is a voltage drop across R downward, which is equal to IR, because V equals IR. But we know that there is also a voltage that dropping in the upward direction from outside the circuit. That means that across this resistor, we get a voltage rise and a voltage drop in this direction. Just like in this version of the circuit, where we get a voltage rise and a voltage drop from A to B. In this circuit, the voltage rise and voltage drop happen at the same place, across this resistor. In this circuit, the voltage rise happens at the battery, and the voltage drop happens at the resistor. To summarize, no matter whether we write this circuit as a voltage source and resistor in series or a current source in parallel, because of superposition, the resistor will behave the same way in response to the rest of the circuit in both the left and right versions. And because all the current entering A must exit B, if we replace the voltage source with a current source that is equal to V over R, this current source will also produce a voltage rise across this resistor that is equivalent to the voltage rise produced by this battery, because all the current from the current source can only go through the resistor, or else it will violate Kirchhoff's current law. You may ask, Jonan, doesn't this current also affect the rest of the circuit? It does, but we can include that in our analysis by saying that that effect is part of V outer, or it changes the way the rest of the circuit operates and results in a different V outer. This can be understood because in the left version of the circuit, of course, this voltage also produces a voltage drop across this resistor, where this voltage affects the circuit and what V outer is. What we are trying to do is replicate the effect of having a voltage rise and a voltage drop, and we can effectively do that by having a current source so that I times R is equal to V. I encourage you to chew on this a little longer if you want, but if it didn't make too much sense, you can always just remember the conversion and focus on the earlier half of this video where we did an example demonstrating how source transformation can be used.